Hey guys, welcome back to my channel. This is Amog from Amog ICSE Insight. So today we are going to do radioactivity of physics, and I'm gonna tell in short the whole chapter so that you can see this video even during your exam time in the mornings for short revision or quick revision. So let's begin. So first of all, what is radioactivity? Introduction to radioactivity and nuclear structure. See, I think you all know in chemistry atom consists of electrons, protons and neutrons. Okay, so atom consists of a nucleus made up of protons and neutrons which are together called as nucleons. I think most of you know that. Next, surrounded by electrons in orbits. See, if you take this as an atom, here there are protons and neutrons, and the electrons surround them in orbits here. Okay, so next, the atomic number is the number of protons and the mass number is the total number of protons and neutrons. Z is equals to E is equals to P. Okay, A is equals to Z plus N. N is equals to A minus Z. Okay, next. And Radioactivity is a natural process where stable atomic nuclei loses energy by emitting radiation. This spontaneous disintegration leads to formation of new elements or isotopes. There are three main types of radioactive emissions. First of all, alpha particles, positively charged, heavy and slow moving. They are helium nuclei, two protons and two neutrons. See, alpha particles have two protons and two neutrons like helium, so they have the nucleus of the element helium. Okay, and alpha particles are always positively charged particles, beta negatively charged, and gamma particles are having no charge. They are neither positive nor negative, they are neutral. Beta are more fast and beta are more fast than alpha, and beta are also known as electrons or positrons, lighter and more penetrating than alpha particles. See, if you take a box of some radioactive element which emits radioactive uh, uh, which goes through disintegration, and if this emits particles, alpha will just deviate right here. Okay, but beta will go till here. Okay, gamma will not at all deviate, they'll just move ahead in a straight path. These are called radioactive emissions: alpha, beta and gamma. Next, if we go with gamma rays are electromagnetic rays with no mass, high penetration and high energy. Okay, during radioactive decay, changes occur in nucleus. These changes often involve the conversion of one element to another by changing the number of protons or neutrons. See, radioactive decay, here I took an element, so this is going through radioactive decay. If this emits alpha, if this goes under alpha decay, so what happens is the isotope or element before two groups of this element is produced. See, now if I take, I'm just giving an example of a non-radioactive element, but you can take uranium. So now I'm giving an example of so I'm gonna take uranium. Okay, wait a minute, I'm gonna take uranium. So first of all, what is uranium? It's a biggest radioactive element in the world. Okay, see, the atomic number of uranium is, okay, wait a minute. I'm just trying to remember the atomic number of uranium. Yeah, the atomic number of uranium is 92. So, when you take a uranium whose atomic number is 92 and its mass number is 238. 238. So when this goes under alpha decay, what happens is the atomic number reduces by 2 and comes down to 90, and the mass number is also reduced by 2, which comes down to 236. Okay, So here what the sorry, mass number is reduced by 4, my bad, mass number is reduced by 4, which comes down to 234. So here what happens is, see, 90, which is thorium, but here 234. So isotope of thorium is formed here. Okay. So next, this is the image suggestion diagram of an atom showing protons, neutrons, electrons. See, it's here. This is a diagram of, like, this is the image suggestion which you can find in Google, or here's the diagram. Just take a screenshot of this diagram. Here I have shown everything. This is these are electrons in the path, and this is the nucleus, and these are atomic particles like beta, proton particles, protons, and these neutron particles. These are proton particles, and these are beta particles. This is atomic number. I just blurred everything due to copyright. Okay, just for copyright. Beta electrons, uh, beta. These are resting electrons, gamma rays, and these are. I don't think these are some kind of race, but as it's blood I can't guess what kind of races. You guys guess and tell me that. And as you all, I think you all have seen the whole diagram. Yeah, as you all have seen alpha and beta decay in the previous what I had showed in the slide, and the picture of alpha particles and beta particles. Now let's get to the equations directly. And I think you all know what is alpha decay. In alpha decay, a emission of helium atom is taken place. So when a uranium atom goes through alpha decay, a thorium isotope of mass number 234 and a helium atom is produced. And in beta decay, a neutron is converted into a proton, emitting a electron. Atomic mass increases by 1 and mass number stays the same. See, when you take a carbon 14, okay, this gives rise to what this the isotope of carbon which has mass 14. When you take that one and when it goes through beta decay, this gives rise to nitrogen, which is of which has mass number 14, and a beta particle which is an electron. So here the electron number changes from 6 to 7, and atomic number remains the same, but the element changes. Okay, in beta decay what happens is a proton is converted into, okay, I have just there's a mistake, there's the same thing repeated, and there's this is the image for that. See, oh wait, whatever. Okay, this is the image of this one. Maybe I don't have an image for this one. Okay, let's get to uses and harmful effects of and safety precautions of radioactivity. First of all, we'll go with uses of radioactivity. Radioactivity is used in medical, industrial, scientific, and agriculture fields. First of all, what is medical radioactivity? See, radioisotopes like iodine 131 are used for treating thyroid disorders, cobalt 60 for cancer radiotherapy. So I think you all know when you go for chemotherapy or other therapies of cancer, they mainly use cobalt 60 radioisotope of cobalt. And next, if you go for industrial use, this is used for checking the thickness of materials, detecting leaks in pipelines. See, when you pass a ray of alpha, beta, or gamma through a pipeline, it emits out where there is even if there is a small hole, it emit it's like it starts to emit out of that hole. So you get to know if there is a leakage in a pipe or if there is any damage in the pipe, and this is also used to check the thickness. So scientific carbon 14 dating helps determines the age of fossils and archaeological finds. Agriculture radioactivity traces improves crop production and pest control. And there are harmful effects of radioactivity. Radiation can damage living tissues and DNA, leading to cancer, genetic mutations, and even death. Long term exposure can affect reproductive health and cause developmental issues. And accidents like Chernobyl and Fukushima have shown the large scale dangers. And safety precautions, use of lead shields, radiation suits, and dosimeters. See, lead is the major element which protects us from radiation. So if you are working, or if you know anyone working in a radioactive plant or a nuclear plant, you will see them always wearing lead on their body. They'll be having lead gloves, lead suit, lead helmet. So what lead does is it absorbs all the radiation and doesn't like allow the radiation to pass through it. Okay, like limiting exposure time and maintaining less distance from the sources of radiation. Proper labeling, handling and disposal of radioactive materials. See, I'll tell you one thing. When there is a nuclear power plant built, when there is a nuclear power plant built, the radioactivity or anything else which is going through in that plant, that waste which produces or which is produced by that plant is disposed in old mines or closed mines where there is not even not even the entry of a dog allowed. Even a dog can't enter those, and it's so far away that neither a fly, okay, flies can enter, neither a small animal nor a human can enter it except specialists of handling those wastes, and except the people who wear lead suits, because it's so dangerous that if you touch it bare hands, your hands may cut may be cut into two pieces. Okay, so next, yeah, let me go ahead with next slide. And this is the types of, okay, this one should be there and that one should be here. There's just a small confusion, guys. Okay, this is the types of radiation: alpha, gamma, beta. Gamma background radiation. Sources of background radiation are rocks, rock and soil. Background gamma radiation, and alpha from space. Alpha radiation is mainly in the space, and beta radiation is mainly from the nuclear power plants. And gamma is also caused by aluminium, beta is also caused by aluminium. Okay, next, radioactivity, radioisotopes, cancer isotopes, yeah, cancer isotopes, which is cobalt 60, as I had said you. Food, guys, it's blood. I think you can understand what's here. Food contamination and warning, yeah, that's it. Next, background radiation, x-rays and radioactive fallout. See, background radiation is the radiation that we are exposed to daily from natural and man-made sources. Okay, see, we are always exposed to some kind of radiation. Every second we are exposed to some kind of radiation. It is called as background radiation. Natural sources include cosmic rays from space, radon gas, radioactive rocks. Man-made sources include medical x-rays, nuclear power plants and nuclear weapons testing. Okay, x-rays are a type of ionizing radiation used in medical diagnosis. While useful, excessive exposure can be harmful, so safety protocols must be followed. See, whenever you go into a X-ray room, there's a board outside telling pregnant women not allowed, small children not allowed, children under the age of 4 are not allowed, or 5 are not allowed. Sometimes there's even 7. As the it depends on the concentration of the X-ray radiation. If it's highly concentrated or more powerful rays, children under 7 are not allowed in there. Okay, radioactive fallout occurs when radioactive particles from a nuclear explosion or accident settle in the environment. This fallout can contaminate air, water, and soil, leading to long term ecological and health damage. I think you all know what happened in Hiroshima and Nagasaki. This is what happened in Hiroshima and Nagasaki, and the people are still suffering from those nuclear bombs dropped during World War II. Okay, fallout can result from nuclear weapons testing, accidents at nuclear reactors, leakage during the handling and disposal of nuclear waste. I have said you before. Proper contaminant monitoring and international cooperation are crucial in reducing fallout risks. Okay. Next, we have nuclear fission and fusion. Wait, why did this come here? Okay, nuclear fission and fusion is here. I think there's today images are totally jumbled, guys. I don't know why. Okay, nuclear energy is generated through the process of nuclear fission, where the nucleus of an atom, typically or mostly they'll use uranium or plutonium, because they are the most radioactive elements, splits releasing a large amount of energy. This energy is harnessed in nuclear power plants to produce electricity. While nuclear power is efficient and emits no greenhouse gases, it generates radioactive waste which is hazardous and remains active for thousands of years. See, nuclear power is efficient and it generates radioactive waste. This waste is hazardous and remains active for thousands of years. Imagine today I generated some nuclear waste. I took it to a dump yard or a old mine and dumped it there. And after 1,000 years, some random guy went to the mine and just imagine he touched it and is totally finished, guys. He is affected from those radioactive rays which are being emitted by that waste. Okay, waste disposal methods: deep geological storage, storing waste deep underground in a secure rock formations. Dry cache storage using steel and concrete containers to isolate spent fuel. Reprocessing: some waste can be reused after extracting useful isotopes. Safety measures: enforcing strict regulations for handling and transport. Emergency preparedness for in case of leaks. Public awareness in training of workers. Balancing energy needs to be environmentally safe. Okay, I'm gonna just erase all the ink so that you can read once. Take a screenshot of this thing, and or I'll be uploading this file in Telegram channel, which is Amog ICSE Insights. Please do follow that channel. The link is in the bio. So let's move to the last page of today's topic. Nuclear fission is the process where a heavy nucleus splits into two smaller nuclei, releasing energy, neutrons and radiation. This process is used in nuclear reactors and atomic bombs. Example: uranium 235 plus neutron gives rise to barium 141 plus krypton 92 plus 3 neutrons plus energy. See, uranium plus a neutron gives rise to barium, krypton, and 3 extra neutrons plus energy. This question had been given in the 2025 board paper for physics, especially, and this is a easy question. But if this comes twisted, nobody can help it, guys. It's very easy. You have to understand. See, first of all, barium is released, and krypton is released here, and here three neutrons are released plus energy. Okay, nuclear fusion. See, fission and fusion. I think you all have read about amoeba, which undergoes fission in multiple fission in unconditional conditions, or when there is no proper condition to go through fusion. My amoeba undergoes fission in 8th standard. I think you all have read this. So just remember, fission means into two, fusion means one, two combining to form one, fission two, one giving away two. Like you can remember this by like displacement, sorry, combination reaction and decomposition reaction. What happens in decomposition? One single reactant gives rise to two products, but in combination two reactants gives rise to one product. Okay, next, fission is easier to control and already used in power plants. Fusion is cleaner and safer but requires extremely high temperatures like those in the sun. See, in there may be a question: what type of reaction happens in sun? And you may be given an option with fusion and fission, or there may be a direct one mark question. So it's the answer is always fusion, because the temperature of the sun is so high that only fusion can appear. Like two elements of hydrogen and helium combine to form a new element. Okay, in fusion, and this happens only in sun. Okay, so the temperature of sun is so high and sun is so radioactive, okay, making it hard to achieve on earth. Both processes are fundamental to understand nuclear energy, its potential and its risks. Okay, I think that's the end of today's video, guys. Thank you for watching. Like, share and subscribe to my channel for the notes. Please read my Telegram channel, Amog ICSE Insights. Tata, see you in the next video. Bye.